Good morning. Let's start our lecture on computer control. This is the 10th lecture. And we are going to discuss a number of features related to parametric identification. In the last lecture, we introduced the recursive least squares estimation algorithm. So let us recall it briefly. Suppose that you have the linear regression model y of t equals to phi transpose t minus 1 theta o plus some noise. Well, theta o is a vector of parameters that you don't know the values, of which you don't know the values, and you want to estimate these parameters, and you make observations on y and phi. If you had not a noise, you could simply add, at least in principle, you could do a number of observations equal to the number of parameters, and you would end up with a system of equations satisfied by theta naught. Now, there are several problems with this. One of the problems is that even if you don't have noise, you can have the matrix can be ill-conditioned depending on the data. So the data is crucial here, remember that. And of course, when you have noise, you probably want to have more points of observations than parameters. So to have more observations than parameters, so that you can have a kind of average effect. So you compensate for the error, which can be sometimes in one side and sometimes in another side. Okay, this is quite qualitative, and later we will see that we will have to impose some conditions on E for our estimate to converge to the vector of parameters that I call theta 0. And then what are the estimators? So you receive data and you assume that this data y of t and phi is made probably, in our case, if you want to identify a difference equation, a system described by a linear difference equation. So phi is a collection of past y's and past u's, past control variables and past output variables. And you update your estimate according to these formulas. Okay? So first, you update this last equation for the covariance matrix. That's the so-called Riccati equation. Then you compute the so-called Kalman gain. This is a vector, and this vector is obtained by multiplying the covariance matrix by the regressor phi. And then with the Kalman gain, you update the vector of estimate. So this formula tells you that the next estimate of the parameters is the previous estimate plus the Kalman gain times this. This is a prediction error. This is what you this is the prediction of error of y given the previous estimate, because this is y of t, and this is what you would expect y of t given the fact that you had an estimate at time t minus 1. And what happens? Actually, you can prove these properties. It takes a lot of pages of computations. I'm not going to do that here. I gave an example, and the idea is that K starts to be large. Okay, and if K is large, you give a lot of importance to this prediction error. And so you force theta of t minus 1 to be adjusted in a fast way, and hopefully to converge to the true value. When you reach the true value, the time between square brackets is small, so theta hat of t is more or less equal to theta hat of t minus 1, and the algorithm converges. Now, for convergence to happen, then k should be small. Okay, so you should start with a large k and end with a small k. The large k makes you converge in a fast way to the true value of the parameters, and the small k prevents fluctuations to appear, because even if theta hat is equal to the true value of parameters, then you have the noise, and you would be amplifying the noise. Okay? So k depends on p, and phi is the data, but p, and p is given by this Riccati equation that of course depends on the data. And what happens? You are decreasing p. So in the beginning, you have no information about the value of theta. So you select the initial value of theta at any value, can be a vector of zeros. And P is a large matrix, say 1,000 times the identity matrix. That's a good choice usually. This means that you have a lot of error in your initial estimate. And then P converges, okay? So P is decreasing. And if P decreases, K decreases. So you start with a large K, and if you have good enough data, P will decrease, forcing K to decrease and the algorithm to converge. Okay, so this is the mechanism. And I gave one example, this example of estimating just one parameter, given this phi was a given function. Okay, and we have noise added to the observations. The true value was 2. And you can see here when you use a gain which is constant but small, so it takes a lot of time, but then you converge to the correct value. If you increase the gain, you converge much faster, but then you have a lot of fluctuations because you are just amplifying noise here. And the Kalman gain is even better because it's large in the beginning, so you converge very fast. You see the blue line, and then it decreases, and you have no variance estimate, almost no variance estimate, or small variance for the steady state error. Okay. Now, and you see here P decreasing. You see here P decreasing. Now, P may not always decrease. If your data is not informative enough, you will never be able to converge. I will give you an example after a short while. And sometimes some of the elements of P decrease and some others do not decrease. This happens when you can estimate some of the parameters but not the other parameters. How can this happen? Suppose that you want to identify a first order system. So a first order system is characterized by a pole and a static gain. Suppose that you excite your system with a constant. So everything is constant. Clearly, it will be very difficult or even impossible. If you take the data in steady state, it will be impossible to estimate the pole, because the pole has to do with the changes of the system. But you will be able to estimate the static gain. Okay, so in this case, P would have would be a 2 by 2 matrix because you have two parameters. And what happens is that some of the diagonal elements of P converge to a small number, and some other elements do not converge and stay high. Okay? Meaning that you can estimate one of the parameters but not the other. Now, another thing is P does not go to 0. P goes to a value that is related with the noise level of the system. Okay? And remember that noise can be from several sources. For instance, numerical noise is also a noise, is a deviation. Noise is all the deviations. Or if you neglect high frequency dynamics in your model, then this dynamics appears as noise. Okay? But we will discuss more about it. Now, there is an effect which is sleeping in least squares, in recursive least squares. What is sleeping? When you converge, so your P is decreasing and your K is decreasing. Okay? Now, imagine that you had good data and this happened. So P, the elements of the diagonal of P decreased. So you have very little error covariance in each parameter, and everything is fine, and you have estimated correctly the parameters. Okay? And you went to the situation in which you are sleeping because your P is very small, your gain is very small. Now, suppose that for some reason your system changes, okay? Because the operating conditions became different. If you have an aircraft, it's not, it changes the flight conditions, for instance. Or if you have a process system, the process started working with different conditions. Suddenly, the excitation of temperature, for instance, is completely different. Okay? What happens? You will need your parameters to converge to the new values because the values have changed. But the gain is very small. So it takes a lot of time for the algorithm for this to happen because you have a very small Kalman gain. So you can observe that this is due to the fact that you have a lot of data, okay, and you have an estimate and a covariance matrix that summarizes this past data. Okay? And now a new point comes, and you are adjusting your estimate based on your past history plus 1 point. Okay? And the standard recursive least squares is quite conservative. It compares 1 point to, say, 1,000 points before of observations. And of course, this last point is changes very little because you have this situation. So if you want to keep your algorithm able to track changes in the true parameters, you must change things. And the change is to give a smaller weight to the deviations, to the output deviations that happened in the past. So remember that the least squares functional is a sum of squares of deviations between the model, phi transpose theta, and the output y. Okay? And you have a collection of these deviations along the history of the system. Okay? And if you give the same weight to all of these deviations, you get standard least squares. Now, one idea is to weight less the more remote observations. So observations that you did long ago, say 500 points ago, are less important than the last observations that you have made. So how can we do that? We can put here this factor, which is a number between 0 and 1, up to t minus k. So k is the index of the summation, and t is the most recent instant. So k ranges from the first observation up to the last instance, from k equal to 1 up to k equal to t. And so if k is equal to t, then you have lambda up to 0, which is 1. So the last observation is weighted 1. Suppose, for instance, that lambda is 0.9. If lambda is 0.9, the observation before the last one is obtained for k equal to t minus 1. So t minus 1 is lambda up to 1. Okay, so it's 0.9, it's weighted 0.9. So 2 observations ago, you would have k equal to t minus 2. So t minus k becomes 2. And you have lambda squared. Lambda squared is 0.81. So you are decreasing. You have this exponential that vanishes when you go to the past. And you multiply, the more in the past this deviation is, the smallest is the weight. Okay? Now, you can do all the computations with it. And you can end up with an algorithm. How can I select this lambda? Well, to have some intuition, we can sum the series of the powers of lambda, which is 1 divided by 1 minus lambda. Okay? So for lambda equal to 1, this gives you an equivalent number of observations, which is infinity. So you are observing since the remote past. If lambda is 0.99, you are observing 1 divided by 1 minus 0.99, that is 1 divided by 0.01, which is 100. So it's more or less that only the last 100 points are important. Okay, the other ones are multiplied by weights that are so small. And you see, you can build this table. Now, the funny thing is that a small lambda is something quite close to 1. So you should be careful, because a small lambda, it's the change is not linear. Okay, say 0.1 lambda equal to 0.1 is virtually forgetting everything. Okay, if you put here 0.1, that's 1 divided by 0.9, that's almost 1. Okay, so you have 1 or 2 samples that count. Okay. So 0.1995 is already only the last 20 samples. Okay, so when you select this so-called forgetting factor, you should be careful and remember this formula, that this is an heuristic. Okay, I'm just doing an heuristic estimate of the number of the samples that count. Now, what is the algorithm? The algorithm is very simple. So these are the new equations. These are the new equations. And in the standard least squares, you had here 1 instead of lambda. And now you divide p by lambda. Okay, remember that I told you, let's go back a little bit. When I deduced the algorithm, this was one of the forms of the algorithm. This was another form that was equivalent. So with forgetting, including that weight that I call the forgetting factor. So when I forget the past data, I replace this 1 by lambda and I divide p by lambda. Okay? And I end up with this algorithm. Okay? Now, remember that lambda is smaller than 1. Actually, the mathematics of, if you want to prove results on these formulas, usually it's quite complicated. But there is one intuition that we can have. You see that you are getting p of t by dividing this function of p of t minus 1 by lambda. Okay, so this is a correction matrix that depends on the data and the Kalman filter, which also depends on p. but this is a correction term, and you have P of t minus 1, and then you divide by lambda. If you divide by lambda, lambda is smaller than 1, so it's like multiplying this by a number which is bigger than 1. So you are increasing P. Okay? So what is happening here? What is happening here is this. You are giving less importance to the past because of the including the forgetting terms of the weights, and this causes K to increase. So the algorithm is more sensitive to the most recent points. But on the other way, you are making P decreasing because you are receiving data. Okay? So your P is decreasing because you are receiving information from data. But on the other side, it's increasing. There is an increasing effect because you are dividing by lambda here. Okay? And so if you want the algorithm to converge, the data must be informative enough, okay, on the parameters. Take again the example I gave you of the first order system in which you want to estimate the pole and the static gain. Now, if you just excite the system, say with a constant, and we have an initial transient, say, instead of exactly being a constant, imagine that it is a step, and a step function. So has one value and then moves from 0 to 1. What happens? There is a transient. During that transient, you gain some information about the pole, but then no more information about the pole is received because you are just seeing a constant. Okay? If you use a forgetting factor, probably your estimate of the pole is going to improve, but then the P corresponding to the pole is increasing. Okay, and this causes the corresponding component of K to increase, and probably this correction becomes very much sensitive to noise, and you are just amplifying noise. Okay, let's see one example. Suppose that your system is given by this. Okay, this is a simulation, and E is a white noise sequence. Remember that a white noise sequence is a sequence made of independent random variables. Usually we take it to be Gaussian, but can be anything, may not even be Gaussian. Okay, but let's assume they are Gaussian, but what is important is that they are independent. So E of 5 is a random variable that is independent of E of 4, E of 6, E of 3, E of 7, and so on. And since this is a simulation, I know the true value of the parameters. And I say, well, A is 0.6 and B is 0.1. Okay. And I use a forgetting factor of 0.95. This is forgetting a lot. Remember, I'm just considering the last 20 samples. And now I do 2 types of experiments to generate data. In one case, U is just constant. In the other case, I add to this constant a noise signal, okay? Noise which is independent of that one. So I generate random numbers independently and I add it to the input, okay? So 2 different experiments. Let's see what happens. This is the first case in which my input is a constant. See what happens. When I apply a constant, there is an initial transient because the system was with a 0 initial condition. It responds to that constant, so it's like a step. And you receive some information, and your A parameter the estimates of the A parameter converges more or less to the correct value. And this happens because due to the fact that you receive this initial information about the system, your P, which is represented here, decreased very fast, very fastly. Okay, but now what happens? You are always dividing your P by 0.95, so you are increasing your P. And on the other way, you are not receiving information on data that allows P to decrease, to go against that tendency of increasing due to the forgetting. So P starts to increase. Okay, you see, P decreased and then starts to increase. And after a while, this increase in P causes an increase on the gain, and the gain is so big that you start to be very sensitive to noise, and you have these wild variations. Okay, so your estimate started going up and down in a way which has very little to do with the true value. Okay, this is the so-called covariance wind-up. Okay, o vendaval da covariância that causes the covariance to go to higher values, and the common gain increases, and then you become very sensitive to noise. Okay, remember, this happened because you were no longer exciting the system in a way that allow you to estimate the true value of the parameter. Now, repeat this estimate, but now use the data obtained in a situation in which you are continuously exciting your system. So you are adding noise. And as you see, you convert to a value. Okay, you have some fluctuations. Okay, this is always a little bit shaky because you are always forgetting, working on the past 20 points, more or less. But you don't have wild variations. Okay, you are close to the true value for the parameter, which is 0.6, and P no longer grows. Okay, because now I still have the same tendency of making P grow because I'm dividing by 0.95, but then I have the other effect, which is I'm receiving information from data, and this information forces P to decrease. Okay? If I reduced, one interesting experiment would be to say, make lambda equal to 1. That's no forgetting at all, standard algorithms. Then this would probably converge to a constant value. Before going on, let me also make a remark. Remember that the covariance matrix P is the inverse of the information matrix lambda, capital lambda. And when you have a forgetting factor, the new information matrix is the previous information matrix attenuated by the forgetting. So you multiply everything by 0.95, for instance, and then you add the new data. Okay, so you forget some of the old information and you add the new information. So the information is being decreased in this first term and being increased in this last term, but provided that phi is informative enough. You want to make some question at this point? Okay. Now, suppose the situation I mentioned in which you change the algorithm, okay? And I change the true value of my parameter from 0.6 to 0.8, okay? And I have here two estimates made with different values of lambda. You see, I have lambda equal to 0.99 and lambda equal to 0.95. And what happens is that when I do the change, with 0.95, it's faster in adjusting the estimate to the new value. And but then, well, this is not much visible here. But if you do longer experiments, typically what happens is that then you have higher fluctuations than the other case with 0.99. So the closer you are to lambda equal to 1, the slower will be the adaptation to the new estimate. Now, just a mention of this type of forgetting is a so-called exponential forgetting, because you have this exponential weight. There are many algorithms about forgetting. And two families of algorithms are variable forgetting factors. And variable forgetting factors act like this. Suppose get your prediction error. So this term here is very small. If this is very small, your estimate is very good. So don't use any lambda. Make lambda equal to 1. Okay? But if you start seeing that this becomes increasing, starts to increase, then you should, this is a symptom that the parameters are no longer correct and you could reduce lambda. So there are algorithms that adjust lambda using the rationale. So when you have the small prediction error, then make lambda close to 1. When the prediction error is big, you need to readapt the value of your parameters, reduce lambda. That's variable forgetting factor. The other thing is more subtle, is directional forgetting. Remember the situation again of the first order system, and you have two parameters, the pole and the static gain. And sometimes you are receiving information in one of the parameters, say the static gain, but not on the other, say the pole. So probably you want to forget in the relation to some of the parameters, but not with respect to the other parameters. Okay? So you have this notion of, in the space of the columns of the matrix P, you are going to do a kind of rescaling such that you forget, you don't lose information in the direction of in the directions where you are not receiving data. Okay, look again at the information update, information matrix update. So this last row, so this is the information matrix. Here you are losing information by just picking up the last information matrix and multiplying all the elements by lambda. So you are losing information, throwing away information in the direction of all the columns of lambda, of capital lambda. Okay, don't confuse the small lambda, which is the forgetting factor, a scalar, with the information matrix, which is capital lambda, this kind of error or something like that, pointing up. Now, you are receiving information that comes with this phi. And this matrix has a rank 1. A característica desta matriz é 1. Why? Because all the columns of this matrix are proportional to one of the columns, because the way you construct it. Okay, you make this matrix phi transpose as a linear combination of the elements of phi with different weights, but we're always picking up the same vector phi, multiplying by different factors, which happen to be also the elements of phi. Okay, but the rank of this is 1. So you are updating the information matrix in just one direction. Okay? Now, for things to work, sometimes you have to receive information in one direction, sometimes in another direction. This seems a little bit complicated, but you don't have to think about directions. Think about data being informative. But geometrically, this is what happens. Now, if sometimes you receive information along some direction, phi, then along some other direction and so on, okay, you will end up with always keeping lambda invertible with all the columns independent from each other, even if you start losing information here. But if you don't, then the wise thing would be not to lose information in the direction of equally in all the directions, in all the possible directions, but just to lose information in the direction where you are receiving. So you modify this formula and you reduce this matrix in the direction that is proportional to phi, the incoming regressor. Okay, these are the directional forgetting algorithms. I'm not reducing the algorithms here. This is just to give you one idea. They are very powerful when you have parameters that are not much identifiable. In adaptive control in particular, they are very useful. But they have one problem. And the problem is that the convergence of standard recursive least squares is very fast. Even, well, with forgetting you don't converge because you are always fluctuating. Okay? But the standard forgetting, exponential forgetting, does not destroy the fast convergence of recursive least squares. Actually, it's an exponential convergence. When time progresses, the algorithms, the error goes to zero in an exponential way. Instead, with directional forgetting, this is not so. So directional forgetting algorithms do not have errors that do not converge to zero exponentially. So they are very good when you have parameters that some of the parameters are identifiable, some others are less identifiable in the same model. These directional forgetting algorithms are very useful for this situation. But when you want to change, you have to track some parameter that is continuously changing, they are not so good because they are a little bit lazy in tracking because of not having any more exponential convergence. Okay. I hope now I have confused you completely. You want to make some questions? I left you speechless. Okay, let's go on. Still another thing. The formulas I mentioned to you, they are nice in analytical terms, but in numerical terms, they are very bad. And this happens because you are making a subtraction of matrices. You see that, let's look again at the formulas. You have this subtraction here, okay? If you use the other form, you still have another subtraction. Let's see. Okay, you have here this subtraction. And it may happen that you have very large numbers in P, and the subtraction is very small. Okay? And if you have to represent numbers in a computer that are, some of the numbers are very large and some other numbers are very small, you start accumulating errors. It's very difficult. So you have to do operations with numbers that have more or less the same scale. So also P must be kept diagonal, must be kept symmetric, must be a a symmetric matrix. And due to numerical errors, it may not be kept symmetrical. Okay, and when you start considering these sources of errors, the algorithm may diverge. The algorithm may diverge. And if you are having a processor, now processors are more and more powerful processors with tiny dimensions. But even though you have a small processor, physically small processor, physical small computer, let's say, computing electronic computing system, they are less powerful than a large one. Okay? So you should be careful with these numerical aspects. I mean, if you do some simulation in MATLAB for the work that you are doing, that's nice using those formulas. But if you want to implement something that is going to work week after week, so your digital time goes to hundreds of thousands or even millions of epochs, and these numerical errors start to accumulate. Okay, so what can we do? We can use the so-called numerically robust algorithms, and perhaps one of the best things is the so-called Biermann's UD algorithm. Okay, Biermann was a NASA consultant. He died, I think, in 1970. And how does this algorithm work? Instead of propagating P, you propagate two matrices, U and D, such P is U, D, U transposed. Okay? D is a diagonal matrix. So D does a kind of normalization of scaling. Okay? And U is a triangular matrix. Actually, it's upper triangular. So below the diagonal, everything is zero. And you have ones in the diagonal. Okay? So what happens? First, if you know that P is U, D, U transposed, no matter the values of U and D are, P will always be symmetric. That's a quite important thing. Okay? Keeping the symmetry of P in numerical terms. And the other thing is that you have this scaling factor that avoids having to deal with very large numbers and very small numbers. And it's very easy to, the algorithms to propagate U and D, they are a little bit more complicated than those formulas, but not much, and it's very efficient. You can even implement these algorithms in firmware, and this is actually something that allow your algorithm to work for years without numerical problems. Okay. The book by Osterman Wittenmark includes a Pascal procedure for this algorithm, which is correct. Okay, you can sometimes the code that appears in books is not correct, but this one is. Okay, and usually the code for this algorithm, the Biermann's UD algorithm, computes P, but what is important is the Kalman gain, and it produces the Kalman gain K as a byproduct. I'm not going to make questions about this, but it's an important remark. If one day you will have to use recursive least squares pop up in many situations, then you will. It's wise to use this UD algorithm, or there are other types of factorization algorithms. Actually, there are many so-called factorization algorithms. Factorization because you are propagating P as a factor of matrices. Okay. Okay. Now, let's look at another thing, which is the effect of colored noise. We know that our regressor, or our regressive linear regressor model includes noise. Okay? And I told you several times that least squares work correctly, produces correct results in the presence of white noise. White noise means that it's a sequence of uncorrelated variables. Okay. Now let's see what happens is if the noise is not white. So I have here a simulation. I have here a simulation in which I have my first order system. I want to estimate A and B. So I observe U and Y. And my noise is a sum of two terms, E of t plus 1 and C E of t. Okay, I'm summing these two terms. Okay. Now, E is a sequence of independent random variables. So if C is equal, this term is not there, and we have white noise. And if you do a simulation, you see this is the I think it was the A parameter, okay, and it's this curve here below, and you are approaching the true value. The true value is this straight line, and you are approaching this. Okay, you have some fluctuations. Probably, if you go afterwards, you will have up and down. You will be staying fluctuating around this true value. Now, if instead C is not 0, but it's 0.95, then what happens? This element here, made of E of t plus 1 plus C E of t, is no longer independent, because you see V of t plus 2 depends on the past element of C. Okay, so C of t plus 2 depends on E of t plus 1. If V of t plus 1 is given by this term, then V of t plus 2 will be E of t plus 2 plus C E of t plus 1. So it's not white. Okay, we will if I had a blackboard here, maybe we could do some computations, but we can return to this stuff later. But clearly, there is a memory of the past in here, so this is not white. And see, look at what is happening with the so-called colored or non-white noise. You are converging to something which is clearly different from the true value. Okay, so when you have colored noise, least squares do not yield you a zero average for the error. So the estimation error is an average which is not zero, an average with respect to making a lot of observations. Okay, and we can do also some computations. You can do some analysis, mathematical analysis to do this. Now, let's see one thing which is difficult. Okay, this is assumably difficult, but let's try to see if we can do some reach some conclusion. Suppose that okay, I will invert a little bit my slides. So I will return to those slides in a moment. Let's consider the situation we had in that simulation. Okay, so this is the difference equation. The only difference is that I replaced t plus 1 with t, but I've delayed everything. So this is completely equivalent to the previous situation. And I'm considering that U, the input, I selected to be also a white noise, which is independent of E. So if I have two random variables that are independent, the product of two independent variables is the product, the average of the product of two independent variables is the product of the, the expectation. Let's be more correct. The mathematical expectation of the product of two independent variables is the product of the mathematical expectation of both variables. Okay? And in this case, since they are independent, this happens and this gives zero. So if I compute the expectation of u at some time times e at some other time, that's the product of their expectations. Since they have zero mean, that's zero. Now, let's remember the formula for least squares that I can write this. This is a non-recursive way. This is a batch way. I can write it in this way. Okay. And then I make the observation that I have divided by n here and here. So this is equivalent of multiplying and divided by n. So that's why you can write it this way. N is the number of observations. Now, I approximate this summation by the expectation of phi transpose. Usually you do the opposite. When you want to compute the expectation, you approximate it by the sum over the sample. Okay. The expectation is the integral of the function that you want, or the random variable that you want to estimate, times the probability density function of that. So this is a little bit complicated to compute. Okay, but I'm going to introduce this complicated. It will be later simple to work with it. And also this other term, I approximate it by the expectation of phi y. Okay, so what is phi in this case? I write my difference equations in this way. So phi is y of t minus 1, u of t minus 1, and the factor of parameters is AB. Of course, I can write this as this transpose times AB column in the opposite form. So that's another possibility. This is the noise. This is the noise. Okay. And so I have to compute this least squares estimate. So this formula here is the formula for least squares estimate. Let's jump 2 slides. So if I replace this by the inverse of this expectation of the expectation of phi transpose, invert, and multiplied by the expectation of phi y. I repeat it here. Okay. Now we have to compute this term, which is the information term, and then to the information matrix, and then invert it, and this term here. So remember that phi is y of t minus 1, u of t minus 1 transposed. So phi is y of t minus 1, u of t minus 1 times phi transpose y of t, u of t minus 1. Okay? And so you multiply this column by this line and you get this matrix here, and you take the expectation of all the elements. Okay? Now, here I have the expectation of y squared. This, let's do an analysis in steady state. So in steady state, this is the power, is the expectation of the square, okay? The root mean value, the square mean value. Okay, so this is a power. So I call it sigma y of square, sigma y squared. Okay, it's a number, a positive number. We can compute it from y, but let's forget it for the moment. Now, this term here, the expectation of u squared, again, it's a number, but by assumption, I'm using a random sequence of u with power 1, such that this expectation of U squared is 1. So I put there a 1. Okay, I could have used any other number, but let's assume it's 1. Now, the off-diagonal elements, they are equal because I can interchange y of t minus 1, u of t minus 1, and write it as u of t minus 1, u of t minus 1. So they are equal. Okay? And furthermore, you see, furthermore, y of t minus 1. Let's look at the model. Go to the previous page. Okay. Comparing y of t minus 1 with ut of minus 1 is the same as comparing y of t with ut. So if I multiply y of t with ut, what do I get? I get the product of ut with y of t minus 1. Okay? And all the elements of y of t minus 1 do not depend on u of t. Okay? Because they only depends on the past. Now I have here u of t minus 1. And then I have the product of ut with t. Now, if you take the expectation of ut with et, for instance, since u and d are independent, the expectation of the product is the product of the expectation, so this is 0. The expectation of ut minus 1, u is a sequence of independent random variables. So ut is independent from ut minus 1. So the expectation of the product is again the product of the expectations. So again, it's 0 because the expectation of ut is 0. And now, this is a little bit more subtle. You have the expectation of ut times yt minus 1. But yt minus 1, if you go on using this model more and more and more, you express everything in ut minus 1, ut minus 2, ut minus 3, and so on. Okay? So ut is independent of this term again. So the expectation of the product is the product of the expectations, and the expectation of ut is 0, so this is again 0. So multiplying yt by ut and taking the expectation just gives you 0. And if you do it for t minus 1 and ut minus 1, that's the same. So these off-diagonal elements are 0. Okay? So your matrix, your information matrix is very simple. It's a diagonal matrix. And the inverse of a diagonal matrix is the inverse of the elements in the diagonal. You can prove it very easily by multiplying these two matrices and seeing that the final result is the identity. Now, I have to compute this other term, phi of t minus 1 yt. Remember that this first part is this matrix, and now I have to compute this other term here. Okay? Now I use the definition of phi, and phi of t minus 1 is yt minus 1 ut minus 1. Okay? And again, I use the model. So let's start by computing the second one, which is simpler. Let's start by the expectation of yt ut minus 1. The expectation of yt ut minus 1. Now, I use the model for yt. Okay? And so I write the expectation of the model times ut. Now, let's take all these products. U is independent of E. So these two terms, they vanish because the expectation of U times E is the product of their expectations that are 0. So this term go away. Now, ut minus 1 times b ut minus 1, that's b expectation of u squared t minus 1. But the expectation of u squared is 1. So this is just b. This time just gives you b. Okay, right there, b. And now you have u of t minus 1 times a y of t minus 1. Now remember the model that y of t minus 1, according to the model, depends on ut minus 2, ut minus 3, and so on, if you go on iterating the model. And so this is 0 because ut is correlated. So this stuff here just gives you b. And now we have to compute the first one. The first one is a little bit more complicated, but not much. And the reason is the same. So use the model for yt and expand it, okay? And what do you get? What do you get? You will get, I should have written here the elements, but yt, remember, let's look at the model, is a yt minus 1, b ut minus 1, et c et minus 1. Okay, so yt minus 1, and then I have a yt minus 1. That's a sigma squared of y. Okay, that's the expectation of y squared at t minus 1. I'm working in steady state, so I just assume that the expected value of y squared is just this constant sigma y squared. Then I have b, expectation of y t minus 1, ut minus 1. Okay, ut minus 1 comes from the model. Again, as before, this is going to be 0, okay? Because y of t minus 1 depends on ut minus 2, ut minus 3, and so on. Remember that there is a delay on the dependence of y and u. So this term does not appear. Now, et times y of t minus 1. Y of t minus 1 depends on et minus 1, and its past. So et is independent of y of t minus 1. So the expectation is the product of the expectations, and the expectation of e is 0. So again, this does not contribute to anything. Now we have the expectation of et minus 1, y of t minus 1, and y t minus 1 depends on et minus 1, and so on. Okay? So you have c and the expectation of the last element, because e will be independent of all the others. If you rewrite again the model here, you will be convinced of that. So this gives you just c times the variance of e. Let's call it 1. Okay, so assume that e is unit power, unit covariance. Okay, so this term is nothing more than a sigma y squared plus c. Let's put everything together. So you have to put the inverse of the information matrix times this term here. That's the least squares estimate. If you do this matrix multiplication, what you get, your estimate will be a plus c divided by sigma y squared and b. Okay, so the expected value for your estimates are not a and b, but they are a plus a term that depends on the correlation of the noise. If the noise is uncorrelated, it is white, c is 0. So if c is 0, if you have white noise, then your expected value for the parameters will be a and b as expected, the true values of the parameters. But if not, your expected value will have a bias, okay? This is a bias, that's a systematic error. That's what was appearing, okay? Any question about this example? Okay, this is not simple. I know probably some of you are lost, if not all of you are lost. Now you can generalize. And this is the objective of these three slides between 197 and 199. And the conclusion is that for the least squares estimate to be unbiased, that is to say not to have this systematic error, the noise must be white. I'm not going to read them because you have been already massacred a little bit. Okay, but the important conclusion is this one. So now we have two things. What happens when we have non-white noise and we want to estimate it? It's the subject of tomorrow. We need methods to estimate models in the presence of colored noise. Now, the other point that I want to call your attention to is that you can think of a controller in which you are estimating your model using recursive least squares and updating your model. That's adaptive control. Updating your control law from the model estimates. So you are continuously updating your model and you redesign your control law. Okay? That's the simplest adaptive control algorithm that you can imagine. And you can say, well, if I have non-white noise, that is to say, I have disturbances that are correlated, or sensor noise that is correlated or something. Now, the funny thing is that when you have a controller, the control is an effect of decorrelating the noise. So noise becomes, remember that a closed loop model or a closed loop system satisfies several models. And one of the model is with white noise. So it converges to your controller parameters will converge to the correct ones to compensate for the correlation of the noise. That's the so-called self-tuning property that probably some of you have heard about, adaptive control, the story of self-tuning controllers. Okay, so later we will speak more about this, and I will give you an example to be more precise. But don't think that, okay, least squares is something that we throw away, because it's a basic, very basic building block of system engineering, not only in control. It's a quite important block. And in particular in control, we have this effect of the controller making part of the work with respect to the existence of covenant noise that allows least squares to be used and yield the correct model. So what have we learned today? We have learned a number of properties on recursive least squares. We have introduced forgetting, okay, the forgetting algorithm, which is quite useful when you want to track parameters that change. And we also have discussed the story of colored noise. Okay. So is there any question? If not, thank you very much for resisting my lecture, and we stop here, and we will continue tomorrow. See you tomorrow.